Speciale and Giorgio from Scality with another episode of our podcast. How you doing, Giorgio?
I'm doing great. What about you?
Yeah, I'm doing well. I think we're really digging into some great stuff here with some of this testing we've done, storage, object storage with GPU and keeping them fed. We did one episode before where we talked about model loading time. I think we want to continue that as a series here with another episode where we talk about the KV cache and how we can supplant that, augment it, and also provide excellent performance. So ready to go?
Yep, let's go.
Okay, very good. So I think the overall thesis we have here is that the GPU memory is small, but we're all hungry, right? We're all extremely hungry. We want bigger context. We want more users, more simultaneous sessions. That means everything needs memory, and that's going to end up being the bottleneck, right? So guess what? We're going to need storage to do this. Okay, so with that, can you remind us a little bit about the landscape in terms of the hardware and software stack?
Absolutely. So still the same lab running on HPE servers. The GPU server has a RTX 6000 Pro, so very recent Blackwell GPUs. They don't have NVLink between themselves, so we haven't done tests where one model spans multiple instances, multiple GPUs, but it still allowed us to do a lot of tests. There's the networking is 100 gigabit. Using a Connect X6, and we have 4 of them, 4 links per machine. So we effectively testing up to 4 times 100 gigabit. Our goal is to saturate the network, and we can do that thanks to RDMA. And all the switching is RDMA enabled. So we can use the hardware to do direct transfer from GPU to flash and flash to GPU. On the storage side, we're running Scality ADI on 6 storage nodes, except one node had a different card, Connect X6, but non-DX, and we were not able to use it in that network. The performance was not as good. So we had to remove one node. So everything that we show is only running on 5, where the nominal is 6, but we're still getting the performance we wanted. So it shows the resiliency of the software, the object storage stack. Okay. For memory, there's 20 NVMe TLC drives on the storage server and 4 on the GPU node.
Yeah, makes sense. Okay. Just for everybody that's listening, Giorgio mentioned Scality ADI. That is autonomous data infrastructure. That's our latest and greatest object storage solution that we announced back in May of this year. Okay, so we'll reference that here as we go through. Okay, so that's the hardware side of it. What about the software stack?
So this test, we wanted to have a real end-to-end stack. Because earlier, like in a few podcasts ago, we showed some numbers and it was benchmarking mostly doing transfer. This time, we're actually using an application like vLLM to load a model. We use Model Express for loading, and we actually apply models and have a token input, token output. So it's a real end-to-end test. Right? Okay. We're using NIXL from NVIDIA for all the data movement and transfer, and our Scality plugin for NIXL, which gives you S3 access to our object, as well as our internal AI API, which we call our native API over RDMA.
Okay. So it's a really stock stack, and we just plug in at the bottom. So it should be all pretty transparent. The other
layers. Absolutely.
Yeah. Okay, great. That's a good context. There's a multiple alternatives for how we access the storage or how applications can talk to storage and the GPU can talk to storage. We have S3 and we have a native API. Can you kind of lay those out for us?
Yeah. So we wanted to compare S3 native API over TCP over RDMA against local storage. And we basically want to be able to tell our customer which interface is the right one per the use case they're getting. So it was very interesting to compare. What's the difference between the native API and the S3 API is the native API has much less overhead. It's much more optimized, but it has less granularity in terms of access control and access management.
Okay. That makes sense. It's a leaner object storage API. That's the way to think about it. Okay. The local NVMe, that's really our baseline, right? We want to kind of compare to local storage against very fast network storage over RDMA. All right. Excellent. We talked in the first episode about this specific test about the model load time. Here we want to talk KV cache, but we're really looking at 3 things, right? Time to first token. This is really to check, compute bound prefill versus accessing from the KV cache. The latency between tokens, and also just generally KV cache. How much can leave the GPU before we start getting an impact? Okay, so those are the 3. Can you kind of set the stage on recompute and restore for our listeners?
Yeah. So when the KV cache goes into storage, you can restore it directly from storage, or you can decide to recompute it, because meaning reparsing the input.
Yeah.
So you need to compare both, right? And in our test, and we're showing more details in the next slide, on a 14K window, so prompt size, we were able to restore in 166 milliseconds when recompute was between 2.3 and 3 seconds. So there's a huge difference. So that means there's a benefit to doing a restore from object storage, which is much faster restore. Yeah. Especially when you do architectures at scale, which have GPU farm dedicated to prefill, which is applying vectorization to the input, versus decode, which is creating the output. You always have to go for the KV cache. So prefill stores into the cache and decode reads from the cache. When you get these kind of numbers, 166, it enables these architectures, because now you can have a stateless farm of decode GPU and a stateless farm, of prefill GPUs.
Yeah. It's always amazing to me how much has to happen in recompute, right? Because for every token, every layer of the model, it has to do this computation, right? It's such an expensive process. So KV cache is going to be a real winner.
Yeah. And when you use some of these APIs online for inference, like OpenRouter or even OpenAI, there's a different cost between cached input and regular input.
Yeah.
That's it, right? Yeah. That's exactly what we're talking about. If we can restore from storage, then you don't pay as much.
It's amazing. I don't think people realize that. We all knew that there was a cost per token, but not that there's a lower cost if the token is in the cache. So that's very enlightening, huh? Okay, so in the end, we ran the tests and get a pretty striking result, right? Because you would think HBM, host DRAM are just blazing and storage is going to be way behind, but it's not that far behind.
So here we are using our native AI API over RDMA. And in that case, Scality ADI, the time to first token, so the model is already loaded, but the KV cache is empty. And so to generate, you have to load the KV cache and then generate the first token. And that's what we measure. Okay. So it took 166 milliseconds. So let's say that it's completely transparent to the user, right? You don't notice these kind of latencies.
Right.
If the cache was in DRAM, it's 102. So we only added 60 milliseconds. If it's already in HBM, it took 83 milliseconds because there's still some processing to be done, right?
Yeah.
To be able to show the first token. So we're very on the same order of magnitude than local memory on the machine. And
this is striking, right? Because for me, you would think that it all of a sudden jumps in order of magnitude, but they're, like you said, in the same. And then you start thinking about all the, simultaneous concurrent access. This starts adding up. But here in the end, we're playing in the same ballpark, right? Just a few tens of milliseconds.
And you think that the capacity on a system like ADI as an object store is infinite.
Right. So now you start thinking huge context, lots of users. It's all going to be very effective.
Yeah. And look at the full recompute cost. So we have a range because to get these numbers, we do multiple checks and we average the result. And there was a big variance in recompute time. So
interesting. Okay. It's a significant variance, huh? So run to run. Okay.
Yeah.
There's got to be some differences there. All right. So that's very impressive. And then we want to talk about the time to first token. Basically, I read this and you can explain it better than I can, that once I get the first token, everything's flat after that. I take the hit once.
Yeah. So it's slightly different interpretation. So in this case, we're having multiple sessions in parallel.
I see.
I think the window is the same, it's still 14K. And we wanted to show that as you add to a storage itself, adding more cache, you do not impact the performance of a session in terms of time to first token.
Okay.
And that's 8 terabytes. We haven't got further, but I don't have the result right now. Maybe we'll update the slides. But basically, the number of objects, because this becomes an object in the backend, right?
Yeah.
So the number of objects has no impact on the latency.
Okay.
In terms of time to first token.
Okay. So as the capacity grows, and here we show it logarithmically, basically we stay flat.
Yeah. And over object storage with different metadata engine or different behavior according to the number of objects could have a different curve.
Yeah. Agreed. It could have started scaling, spiking up. All right. So what I said a minute ago then still sort of is true, right? The first token has to hit storage to hit from the KV cache, but then you're in the GPU memory.
Yes. And so that's one of the artifacts of how our test has been designed. You could imagine that maybe you're evicting a KV cache from a running session, and then you have to get it from the cache again. but we haven't simulated that. So
okay, got it. Makes sense. All right, so then we have to think about decode, right? And like you and I have talked about, decode happens a token at a time. You would think that there would be some spikes in the latency, right? So ITL is inter-token latency, but we did not see these spikes, right? So it's basically flat, you hit it once, and then you sort of get this predictable flat performance. Is that the right interpretation?
yes.
Okay. And the 166 millisecond, which was the 64 millisecond behind DRAM, is the number. So first token, it lands, and then everything else, you're in.
So if you see that test, you see that Mistral 7B, for example, the bottom one, right? The code path is the KV cache was in storage here on S3.
Yep.
That gives you a time that's longer than if it was already in memory, which is the warm path. And the delta is just the time to get the KV cache for one time into memory. And then you see that it doesn't impact the overall performance of queries.
It looks extremely stable, right? Because you're getting a 4 millisecond variance, 99th percentile. So it's like ultra predictable. Yeah. Okay. Very impressive. All right. I know we said that the software stack is very standard. It's open source, but we did find some things that we had to fix. Is that right?
Yeah. So when I asked the engineers who did the test, what was the biggest challenge you had, right? I was expecting some issues on our RDMA implementation. And now what came back is they had to fight the stack itself. So bugs in vLLM, Model Express not being able to load certain models, like FP8 was creating some issues. It's not parallel enough. So sometimes you would see no usage on the storage, yet it wasn't as fast as it could be. Because there was no parallelism. So if something is split into 1,000 objects, you want to load them 100 at a time. You don't want to load them one by one. So some of the stack wasn't optimized. So they had to do some changes into them. Also in a NIXL, even in a Q object has a tendency or is configured to only use one NIC when we had 4. So we had to do our own changes to be able to use all 4 devices because we want 400 gigabit networking. And so there was a lot of not fighting the stack, but optimizing the stack.
Yeah.
And one thing that's clear to us is we want to do that in the open.
Okay.
So if you go to the next slide.
All right, very good.
Everything that we touch has been open, the pull request online. It's on GitHub on the respective project. So we're all doing this in the open and we're not forking anything.
Okay, that's great news. You hate to be that guy to observe it, but it sounds like we're pushing the envelope because these bugs would hit anybody, right? So this is new stuff, and we really end up finding these things.
Yeah, I think RDMA object, this kind of parallelism, it's new to the stack, so it has to be optimized for it.
Okay, well, it's exciting, right, to be at the forefront and be kind of the pioneer. So great stuff, in addition to the good performance. All right. Thanks, Giorgio. That was very interesting. I think we have a lot more material to dig into as we do more and more tests. So we'll come back to our audience and share more as they arise. Thank you very much.
Thank you.